Yeah, it's hamstring right now. Okay, thank you. All right, optimization. Okay. All right, everybody. Optimization is the process in which you find basically the essentially the best way to do something. Okay, hence you optimize it. Okay, with optimization, okay, what you've got going on is basically how optimization works is you're going to have like an equation that you're going to take the derivative of, and you're going to set that derivative equal to 0 and solve. Okay, so it's basically applying the first derivative test to a normal system. Okay, there are some guidelines to follow when doing optimization problems. Okay, and people find it to be tricky to do, but it's usually not the calculus which is tricky. It's usually just figuring out exactly what they're after. Okay, but the guidelines are as follows. Basically, what you want to do first with optimization is basically you want to identify all given quantities, okay, and all quantities to be determined. Okay. Also sketch if possible, or also sketch the system. So in a lot of ways, it's a lot like what we did with related rate questions. Okay, where we figured out what we had, what we needed, and we drew a picture of the system. Okay. Now, the second thing we're going to do here, okay, is write a primary equation. Okay. Okay. That models the system. Okay. Okay. This primary equation, by the way, is going to be the equation that we take the derivative of to find the maximum or minimum. Okay. So basically, you can make a note here that this is the equation we're going to take the derivative of. Okay, so keep that. So the nice thing about this is it's going to be when you identify that primary equation, that's the one we know we're going to take the derivative of. That's what we're going to find the maximum or minimum of. Also, too, sometimes they will give you this equation. Okay, so sometimes you'll have a problem where they just straight out say, you know, the system is modeled after this equation. You know, maximize it or minimize it. Okay, so that's something to note. A lot of times you do have to create this equation yourself. So again, it's going to be something usually simple from geometry. Okay, so something like a circle, or something like a square, or something like a rectangle, or something like a triangle, something like that. Okay, or a simple volume, or something like that. They don't ever make that. They never choose something that's all that crazy. So you don't have to worry about, for example, memorizing the formula of a hexagon. Okay, they won't be a hexagon. Okay, it'll be a rectangle, but not a hexagon. It'll be maybe a cube or a box, but not like some weird jumbled equation. Okay, so very much like we saw with related rates. Okay, all right. Definitely want to review that. Okay, the next thing we're going to do here, okay, is once we've identified the primary equation, we want to reduce and rewrite the primary in terms of a single variable. Okay? So, if you remember, sometimes when we did related rate questions, we had to figure out what one variable was in terms of another. For an optimization question, you're always going to be doing that. Okay? You're always going to be rewriting or reducing the primary equation in terms of a single variable. Okay? Which is going to be very helpful for us when we do this. Okay? that means then that you often have to use use a secondary equation that relates everything together. So often, come on, I hate this stupid dead spot before. Okay. This requires a secondary equation.
Is the primary just primary equation?
Yes. That relates the variables. Okay, so what this equation might be something like a simple ratio. Okay, maybe I know something about the relationship between, on this triangle, I could use this ratio to figure out, what one of the variables could be. It could also be given to you. It could also be a situation where I have to use some other thing that I know. For example, I might be trying to optimize area of a rectangle. Well, I might know the perimeter of the rectangle and use that to whittle down variables. You'll see how it works, but basically, you're always going to reduce and rewrite the primary in terms of a single variable. Okay? Any questions about that so far?
Does it say that relates?
Yeah, that relates the variables. Okay. So basically, you don't want to choose a secondary equation that has nothing to do with your variables. You want it to relate the two variables together, or the three variables, or however you have. Okay. All right. Kind of the next step here. Okay, we call this step 4. Okay, is when applicable, or necessary, identify the domain or values that make sense for the system. Okay. Now I say when applicable or necessary. Sometimes you don't have to do this. Okay. Sometimes it's something you don't have to do, and you just go ahead and just chug away at it. Sometimes though it's necessary to just recognize when a system makes sense. For example, if I'm optimizing area, okay, if I were to get a negative number, would that be appropriate?
No.
Why?
You can have no area.
You can't have negative area. You can have no area, but you can't have negative area. Okay, so it's like things like that. Okay, you might end up with a situation where you get two different answers. You get a maximum and a minimum for our system. One of them is clearly going to make sense. The other is going to be clearly wrong. Okay, and it's things like that you want to be able to identify. Okay, and it helps just to have a good notion of what your system does. For example, if I was working on, again, an area question that I had a known perimeter of, okay, if the area made it so that way the dimensions made it so that were basically made it so the perimeter no longer worked, then obviously that area is junk, right? Because I can't use it if it doesn't work with the perimeter I was given. So it's things like that you want to keep in mind, okay? Most of the time it's very common sense, okay? If I'm doing like an area, for example, the smallest I can have is 0, okay? If I'm doing like, things like that, okay? So bear that in mind, all right? The last thing to do here, okay, is take the derivative of the primary, set equal to 0, and solve. Okay? And that's how you would find your solution to this thing. There's one more thing I want to add. Okay? I'm going to call this actually, I'm going to scooch it all up and make this rule 0 for this. Okay? Okay? Rule 0 is going to be read the question and note what they actually want. okay? I will tell you this right now, the vast majority of problems that people have with optimization questions is not that they don't know how to do them. They'll do it just fine, and they'll figure out all there is about to figure out about the system. But sometimes they forget exactly what the question's asking for, okay? And you'll see this a lot, okay? Where the question will be like, what are the dimensions of the box, okay, that has the maximum volume, okay, with given whatever the constraints are. And they'll figure out the maximum volume and be like, I'm done! Except what do they leave off? The actual dimensions, basically what the question is actually asking for, okay? So it's very important to read these questions and know what they want, okay? Because it's a lot more than just, we optimize the system and we're done. Usually they're after something else. And so you want to make sure you go through the process, okay, I finally optimized it. What are they looking for? They're looking for this. Okay, here's where that is. And you just, make that happen, okay? Everyone got that? Yeah, I can very much scroll down. Okay, so read the question, figure out what they want. Okay, tell me when to stop.
Just go to all the way.
All the way down. Okay. You have class with sound effects today. Sound effects.
Mr. Dowell, I like that play last minute.
Good.
Your
Mr.
play was
Dowell,
much
you were
better.
like the best.
Your play was.
Oh my god.
Your play was much better.
That's good. I'm glad you like the Survivor. The Survivor is definitely the more emotional of the two. That play is depressing to look it out.
Yeah.
It made me
And
think
you
a
kind of
lot.
know the ending, because if you know your history, you know the ending. Which is, but still.
It made me think of that lady we had come speak last spring.
Yep.
And just like the fact that she literally experienced exactly what they were depicting.
Yep. I know I've met and have artwork from an artist who was about 10 or 11 years old and fought in the Warsaw Ghetto Uprising. And so his stories about it are not.
10 and 11.
Yeah, he was pretty young.
Any fault?
He actually fought in it. In fact, he's on one of his hands. He's missing like half his fingers because he was shooting at he was basically shooting a gun at Germans, and the homemade bullets in it, one of them exploded and backfired and basically took the ramrod out and just took off his hand, basically. So, yeah.
Wait, so was TH supposed to be funny last night?
He was so funny.
Like, I don't know if he was, but
Well,
Some of his quotes are.
Yes, there are some things which they purposely put in there to be humorous. Okay.
But his entire character is not the
Other ones
Yeah,
are
not
just
the
like-
entire characters,
The
right?
other ones are just so depressing.
They're both depressed. I mean,
I don't know
it's
if
like about the Holocaust. Of course, it's
But why would they do that?
Do what?
Why would they do super depressing plays?
Because we're doing it because it's like the 70th anniversary of all that happened this year.
That video that they showed.
The 70th anniversary of the end of the
Yeah,
war.
the video was.
That video was so graphic.
Yeah, well,
Wait,
I saw it before that.
All right.
Yeah.
Which video?
In the Black Box one?
Yeah, other people laughed at it.
Let's move on, guys. Okay. So
Yeah.
you get the idea here that optimization is going to be a process. It's not actually just a simple matter of you follow these guidelines. But otherwise, the equations and the questions can all be different, very different. So what we're going to do now is we're looking at examples of optimization problems, so you get to see how they work. Okay. Let's start off with a very easy one, and it's an old standard. Okay. A farmer. Okay, is making a cow pen. Okay? He has 5,000 feet of fencing material. Okay? What are, I should say, the dimensions of the largest rectangular pen he can make? Okay? All right. So there we have. So step one, or step zero, let's make sure we read the question, figure out what they want. Okay? So we got a farmer, he's making a cow pen, he's got 5,000 feet worth of fencing. You know, what's the largest rectangular pen he can make? The dimensions of the largest rectangular pen he can make. So we're not after actually what the area is, we're actually after how long, what is the length of the sides for the biggest area, okay? So keep that in mind. Our answer is not going to be the area, it's going to be the length times the width, whatever that is, okay, for this rectangle. All right? Now, let's see what we've got. The only thing we have, number-wise, is the perimeter. The perimeter of this cow pen is going to be 5,000 feet, okay? Because that's all we've got, okay? So, the other thing that we've got is that the shape of this thing is going to be a rectangle, okay? So, first thing we need to do is come up with a primary equation, okay, that maximizes area. So, what's the area of a rectangle, anybody? Length times width. So, we've got the area is equal to length times width.
And this is our primary equation?
That's our primary right there. Okay. Next, we want to know, we've got to somehow relate length and width together with what we've got. We've got the perimeter, right? It's 5,000. So what's perimeter? 2 length plus 2 width, right? So we've got that 5,000
Is that our second?
is equal to twice the length plus twice the width. And that's our secondary, actually. Okay? So to answer your question, Jim, yes, there is a secondary equation. It's the perimeter. Okay?
Like square also?
Oh, squares are rectangles, right? Yes, so it actually, and you've already figured it out. In fact, actually, this system is maximized when we make a square out of it. Okay? Well, we can't quite yet. Okay? What we got to do first is actually create the, it's not the square root of 5,000 that makes it happen. But because the 5,000 is not the area, it's the perimeter. So we can divide it by 4 and have it work. But the problem is we don't know that for sure yet. Okay? Your intuition is intuition is smart, and indeed this is going to be a square. But we want to show why it's a square, basically, using calculus. Okay? Anyway, so we've got a primary or secondary. So what we want to do now, we want to rewrite the primary in terms of one of the secondary. That is, get this so we've got a single variable here. Okay? So, which do you like, L or W?
L.
You guys like L, so let's solve L for W. Okay? We go ahead and do that, so it's 5,000 minus 2W is equal to 2L. So what's L equal to? 2,500 minus W. Okay? There we have it. So now over my primary, I'm going to replace L with 2,500 minus W. Okay? So my area there is 2,500 minus W times W, which, what do we get when we work that out? 2,500 W minus W squared. So that's my area equation with a single variable now. Okay? Everyone catch that? That's what we're after. That's what we want to do when we optimize. Okay, next step is, we're going to take the derivative of this. Okay? Is that a hard derivative to take? No. The other thing too is, when you do the derivatives for an optimization question, you don't do them implicitly, you do them explicitly. The variable we're going to take the derivative with respect to is W. Okay? So we don't have to worry about the dW type thing. Okay?
Do you always take it with respect to what you're trying to find?
Yes. Okay. You're always, with an optimization problem, you're always going to take the derivative with respect to whatever that single variable you find is. Okay? You're not going to see at this level these done implicitly. Okay? Maybe when you're all, if you ever take high enough math courses in college, you might see an implicit one of these. But at this level here, for the A, B, and BC exams, they're always straight up explicit. Yeah?
I have a couple questions.
Okay.
Do you
Just answer the question. Come on.
do you always when you're like finding that single variable,
Uh-huh.
do you always use the secondary equation?
Yes, that's what it's for.
Okay.
Okay. Remember, there are times where you don't necessarily need the secondary equation,
Okay.
but the whole purpose of the secondary equation is when you need to get it down to a single variable, that's what you use. Okay. Basically, you create a primary, and then you see, okay, what do I need to get rid of? Can I relate that with another equation? The answer is generally yes, and that's your secondary. Okay.
Okay. And then I'll figure out my other question.
Okay. So we get it down to here, we take this thing's derivative. Derivative is going to be dA over dW is equal to, what's the derivative of 2500W? It's 2500, right? Minus derivative of W squared is 2W, okay? And remember, we're going to optimize this, which means we're going to set it equal to 0 now. So we don't care, when you think about it this way too, dA over dW is supposed to represent a change in area. Does my area ever actually change? No, so it becomes 0, right? So we write that as 0 equals 2500 minus 2W. Well, we just have to solve that. That's easy enough to solve, right? 2W is equal to 2500. W is equal to 1250. And our dimensions was always in feet, so we should probably have put that throughout. But as long as you recognize it, that's what matters. Okay? So, the width of this cow pen is 1,250 feet. Okay? So that's one dimension we got there. Now we got to figure out the dimension of the length, but it should be pretty easy. If the width is 1250, and this thing is supposed to be a rectangle, what's the length also going to be? 1250. If we plug 1250 back in up here to our secondary, 2500 minus W equals L. So that means 2500 minus 1250 equals L, which means L should be 1250 as well. So our dimensions are as such. Okay? Here's our dimensions. Okay? So those are the dimensions that optimize the area of the cow pen. Okay? So we're going to make it 1,250 feet by 1,250 feet. Okay? That's a pretty big cow pen, isn't it?
Yeah.
It's almost a square mile. Okay? Yeah?
And will you always be given like some number that would be whatever the secondary equation is equal to?
Yes. And I'm wrong, it's not almost a square mile. Sorry, a square mile would be 5,280 feet times
That would be
5,280
almost.
feet. Still, it's pretty big. It's a large.
You've got almost a mile of fencing.
Fencing, yeah.
Mr. Dowell?
Yeah.
How would you do this? Let's say like they said one of the pen walls had to be like there was only enough space for like 800 feet on one wall.
Okay, well you would decide which wall would be the 800 feet, cap it off there, and figure out the other one. If we're still making this out of a rectangle, that makes life very easy because then there's only one rectangle that's going to work. One side's 800, another side's 800, and the other two sides are 5,000 minus 1,600 divided by 2. Okay, so that makes life a lot simpler if they did something like that. Now you do have situations where there are variations on this particular type of problem, where it's, in fact, I think your AP question that you have on this is going to be one of those variations, where they have this fencing and they want to divide the pen into two, or one side of the pen faces up on a river and so therefore doesn't need any fencing, or faces up on a building that we don't really know. Well, it's funny because they always say, oh, it faces up against the building, and the buildings end up, you're going to maximize it. It's just assuming, I guess, the building is this long, infinite block of building, because buildings usually stop at a certain point, but don't tell you when the building stops. They just say, you're up against the building, it doesn't matter. So, I don't know. I've never understood that version of it. But just assume the building is as long as it needs to be in order for this fence to work. Okay? But you'll get variations on that. Or you'll get variations where the farmer wants to create two pens, I guess one that's a square shape and one that's a circle in shape. Okay, and then you have two different equations that you're trying to work with. Okay, but they can all be done. Okay, so basically those would be tougher versions of this very problem right here. Okay, yes.
I go to the restroom.
You may use the
I've never seen
restroom.
a circular
Okay.
cow pen.
I'm sorry.
I've never seen a circular cow pen.
Yeah.
You haven't? Mr. Dowell, have you seen the Woodbury Forest picture of you?
Okay. Yes.
Oh.
Have you seen what Jim Wilcox commented on it?
Oh Lord.
This one.
Let me see it.
Yeah. It's really,
Wait, is it on Facebook?
Oh yeah.
yeah. it's
What's
on
this
Facebook.
of? When did this happen?
Dowell Junior, Dowell the third.
Oh, I think this is when she was taking.
Did you see the comment?
This is
Wait, what is it?
Hogan.
Hogan. Yeah.
Is this on Facebook?
Yeah.
Everyone like it.
No, Jim Wilcox commented on his feature.
Nice.
He's like, Stephen Dowell is the man. I see a promotion in the future.
Yes, whatever. Alright. Sorry, but I don't have time to worry about that right now.
Everyone likes Jim Wilcox.
Okay,
Yeah, he's the man.
so we got this, so basically this is an example of it. Let's look at a harder example, okay? One thing that can often happen with these types of problems is that we may not necessarily be after something as simple as just figuring out dimensions. Sometimes they'll throw in a different notion, an idea of making something weighted. What I mean by weighted is they'll have some external influence on the thing that adds another level of constraint to the sides. Okay? For example, maybe building the fence, maybe he has to use two different materials to build this fence. One side has to be a rock wall, which costs a certain amount, but the other sides have to be regular fencing, okay, which costs a different amount. What's the maximum way of doing that?
You have to add an equation to that?
Well, you may not necessarily need to add an equation. What you do have to do, though, is weight the values before you take the derivative. Let's take a look at an example of one of these types of problems. This is one I did earlier, okay? Basically, we're going to build a box, okay? We are building...
So this is a separate problem.
Yeah, this is a new problem, new example. A box, okay? It's a rectangular box, put it that way, okay? Box that must have
I don't think so.
a volume of 50 cubic feet, okay? So the volume of the box must be in cubic feet, okay? One other thing about this box is that the length of the base of the box is 3 times the width. Okay, so that is L is equal to 3W. Okay, so they're letting you know a little bit of extra constraint. Okay, now here's where the big constraint comes in. Okay, because if this is what we've got, that's fairly easy to figure out how we should optimize this. Okay, all right. Here's the next part, though. Okay. The thing is, what we want to do, okay, is we want to basically, the material to make the box costs $10 per square foot for the base and lid. And $6 per square foot for the sides. We're building a very expensive box here. Okay, not a cardboard box, obviously. It's made out of like ebony wood and oak and things like that. Okay, for the sides. Okay. Okay. What dimensions give us the cheapest box?
Wow.
This is a lot of restrictions with Dowell.
Well, so this is everything you got. So let's start organizing our information, okay? We've got a volume. We've got a relationship between the length of the bottom of the box and the width of the bottom of the box.
Is that $10
Yeah, $10
per?
per foot squared, okay? And then we're told material to make the sides of the box has a cost, okay? Which means we're talking not about volume at that point, but about what?
Talking about the area.
Surface area. Hint that we know we're talking about surface area? It's feet squared, not feet cubed, okay? So, what we want to go ahead and do is write out our equations and start to fill out everything we know, okay?
What does that
That's 6
say?
feet squared per side.
Yeah, 6 feet.
$6.
$6 per square foot, okay?
What is that base and
Lid.
lid?
The top of the box. Bottom of the box and the top of the box, okay? Okay,
Alright.
let's go ahead and start filling out what we've identified what we know. Again, we're looking for dimensions. Okay, so we don't really need to necessarily know, well, we actually know the volume. The volume of the box has to be 50 feet cubed. So let's go ahead and fill that in. We've got 50 feet cubed is equal to the height of the box times the width of the box times the length of the box, which remember was 3W. Okay? That was given to us. This is a box. It's a rectangular solid. Rectangular solids are base times width times height. Okay? So, H. So that would be the equation for that. Okay? The other thing we've got is what we're trying to maximize or minimize actually is the cost of the surface area. Okay? Before I go any further though, okay, because we're going to write the surface area equation. And surface area, there's several different ways to model it. We're going to model it a very easy way for us, just because it's easier to see what's going on, which is really, surface area is the area of the base and the height together, so 2 times area of the base, and then 2 times the area of each of the, 2 of the sides, basically, okay? The other way to do it is actually do twice the area of the base plus the perimeter of the base times the height. Will also give you surface area, okay?
Secondary equation.
Yeah, this actually ends up being our secondary equation. Good.
Good job.
Okay? Our primary is going to be the surface area. Okay? Before we go ahead and just gun-ho write out what the surface area equation is, though, we want it to have only one variable, right? Okay?
We can do the derivative of something to get the surface area.
Well, not yet. Hold up.
Thanks,
Okay?
man.
You're thinking of a sphere. Derivative of sphere is our surface area. No, we know what the surface area of a box is. Okay? But I'm holding off on writing it fully out because how many variables do I have right now?
3.
2. How many do I want?
1.
So what do I need to do?
Solve H in terms of W.
Solve for H in terms of W. Okay? So cleaning this up, I'm going to have 50 feet cubed is equal to H times 3W squared, which means H is equal to 50 feet cubed over 3W squared. That sounds like a 3WB or something, like a cheesy local television station. Okay, 3W squared. Yeah, right. Anyway, now we can write out our primary, our surface area equation. Okay, so the surface area is going to be twice the area of the base times the height. Or twice the area of the base, which is going to be length times width. So 2 times W times 3W plus 2 times the length times the height. So the height was 50 feet cubed over 3W squared. So 50 over 3W squared times the length, which was 3W, plus 2 times that same height times W. Okay? So 50 over 3W squared
Will we be given that equation?
times W. No, you should
Damn.
What does that say?
you should know what surface area of the box is.
3W squared, dog.
Okay, surface area, remember, is twice the area of the base
Surface area.
Times 20.
times plus twice the area of one side plus twice the area of the third side. Okay.
It's just easier to base.
Yeah.
And there's 6 bases.
What is the first parentheses thing?
That says, so the first parentheses for my surface area here,
Base, width,
that says, sorry, let me move this out so it's clear. Okay.
God.
Alright. So the base of the box is length times width. Length was 3W times the width, which was W. That's the bottom of the box. It's twice because both the bottom and the top of the box use that measurement. Okay? Plus, we're going to do like one side panel. That's going to be the length times the height. So it's going to be 2 times 3W, 2 times 3W times 50 over 3W squared, because that's what we figured out the height was, plus the other side, which is 2 times W times 50 over 3W squared. So bottom, length times width, one side, length times height, other side, width times height. Okay, and that's the surface area. Okay? So that's the equation for the surface area.
So the first one's the height.
Yes.
Height.
Okay. Now, here is the issue though. we have an additional set of constraints on this surface area, don't we? Which is what? The price of making each side.
Oh.
Okay? Now, this is not as bad as it seems. Actually, we're not interested in what the surface area comes out to be, but what the cost of the surface area is. So I'm going to modify this to make this, I'm going to use the same exact equation, but add in the costs. So I'm going to call it surface area cost. The base costs $10 per square foot to make. So I'm going to take the base here, which comes out to be 6W squared, and times it by 10. Okay? So it would be 10 times 6W squared. Okay? Plus, now the lateral sides are each times by 6. Cost $6 to make those sides.
Which, how do you know it costs 10 to make for the height?
This is what it says in the
It says
thing.
the material.
Yeah, the material to make the box costs $10 for the base and the lid. This is the base right here
Per foot squared.
per square foot. So it's 10 times however many square feet that is. Okay?
No, for the height, so I was thinking.
Alright? Okay. Then we do the same thing for each of these, but we use 6 because that's what the sides cost to make. $6. Okay? So clean this up a little bit.
100.
3W times this right here. What's going to happen to the 3W and 3W squared?
Cancel the
They cancel, leave me 3W. So it's
50 over 3W.
it's 50 over W, not 3W.
Oh, yeah, 50 over W.
Times 2, which is 100
100 over W.
times 6. So it's 600 over W. Plus, same thing over here. Okay? 6 times 2 times 50 over 3W. Okay? So that's going to be 6 times,
Wait, why is it 6?
600.
hush. Okay, so it's 600 over 3, which is 200 W. Now what's your question? Okay, sorry, what's your question now?
Never mind, I got it.
Okay,
Kind of late.
alright. Sorry, I don't mean to hush you, but we're like in the middle of calculating something.
Yeah, I got it.
Okay, I gotta get through it first, okay?
Why is the first one 6W squared?
So what's your cost?
3W times, so it's 2 times 3W times W, which is,
I'm gonna.
2 times 3 is 6,
You have to go over like
Yeah.
5 more.
so it's 6W squared, okay? And I didn't fully multiply out, so it's 60W squared. We fully multiplied out. So let's go ahead and do that, 60W squared, okay? So, that equation there now, we finally derived the primary equation we need. This tells us the change in cost of the surface area, okay? So, what am I going to do with that equation? I'm going to do what? Take the derivative, okay? And set it equal to 0. So we'll save ourselves here. Be 0 is equal to 120W. Now this is interesting here. Instead of doing these as quotient rules, can't I just bring that W up as W to the negative first? And then do a regular power rule to it, right? If I did that, I'm going to have minus 600 W to the negative second minus 200 W to the negative second. Okay? And that'll be a lot easier to work with than having that be a full-out quotient rule. Okay? Also, too, now what can I do to those values? I can add them together, right? Isn't that minus 800 W to the negative second?
Yeah.
Yeah. So let's do it that way. Okay?
Wait, why would it be -1 for those
Do
things?
the power rule.
Because it's just W.
I'm bringing them up. I've taken the derivative at this point.
Oh, okay,
Yeah.
you're taking the derivative. Okay.
So here's where we started. When I took the derivative, that became 0. 120W. -1 times 600 to the W to the negative second, which is negative 600 W to the negative second. Same thing there. Okay? Alright. Let's finish this out here. Okay? So, to make life easy, I'm going to move the negative 800 W to the negative second over here. And when I do that, I'm going to go ahead and send the W back downstairs. Okay? So that's going to give me 800 over W squared is equal to 120 W. How am I going to get rid of that W squared? Cross multiply. So 800 is equal to 120 W cubed. Divide both sides by 120. To get W cubed is equal to